Testing on YouTube. Testing on YouTube. All right, works on YouTube. The last one that's left is X. Testing on X. It works on X as well. Perfect. Okay. How's it going, Cheb Khalid and Brian Tang? I'm trying to wear this Yoda costume, which is really just like a little baby hat, but the video removal is removing the ears. So it just kind of looks like a see-through beanie. It's a bit weird, but we'll leave it on. All right, let's get started. Welcome everybody to another Hoopo's stream. Today's stream we're going to go over RAG. So RAG stands for Retrieval-Augmented Generation, and it's a pretty generic term, which means that there's a lot of different approaches that if you really think hard enough, you can think of them as RAG, right? And recently in the news, we've actually gotten to play with one of the more... Wait a second. The audio is coming out of some random thing, and it's making me difficult. Okay, there we go. Okay. So recently, we've gotten a pretty powerful RAG system released. Here's Sam Altman hyping it up. So he's known for hyping his own products, but now he's saying that this time it's really good, and he's referencing specifically GPT-4o now has browsing capabilities, which is a type of retrieval augmented generation, and it's a category that right now has been dominated by obviously Google and Perplexity, right? But unfortunately, this is a little bit hallucinatory. So I took this picture of this robot arm with a camera on it, and I asked, where can I buy this? And this question was actually a trick. So this is a picture of a robot arm with a camera on it from a Chinese startup called Recamera, right? And this is a very early startup that if you kind of just look at the different products that they have and the different offerings, you see how this is basically 3D printed. This is a very early stage startup, right? So I'm pretty sure this robot arm, you can't really buy it, right? So if you actually look at the listing for this, this is not a listing to buy the arm. This is a listing to buy the camera. So I think this startup really only sells the camera, and then within their office, they probably have a single one of these robots set up with this camera that is more of like a demo or a prototype machine. And if you really wanted to buy this, you would have to basically personally email probably the CEO or the CTO of this company and ask them, hey, I'm interested in this robot. And then you'd have to go through kind of a whole negotiation, kind of relationship building process to even get to the point where you could buy this and they would feel comfortable making more of these robots because they think there's some amount of customer pipelines in there, right? So this robot is not actually for sale. That's the trick question. So when I ask GPT-4o, where can I buy this robot? I know that I'm testing it, right? I'm testing to see if, hey, this is not actually a thing you can buy. And unfortunately, it miscorrectly identifies this as the spot arm, right? So Boston Dynamics, which is a robotics company in Boston here in the US, they make this spot robot. And then the spot robot has an optional accessory called the spot arm. But this arm is not the same as this. It's not the same robot arm. It's not even the same end effector. This is a camera. That's an actual gripper. So hallucination there, which isn't good, right? Because the whole point of retrieval augmented generation is that it's a way of kind of reducing hallucinations, because you can fetch relevant information and then use that information to kind of add context to prevent hallucinations. But here it's literally hallucinating. And I give it a little bit of a push in the right direction. I say, okay, this is a re-camera arm. So I give it this string here, which should be important, because that should be all it needs to at least get to a page where it can maybe notice that there isn't an actual re-camera arm. Like I said, I don't think this is an actual arm you can buy yet. And it hallucinates again. So now it says the HTC re-camera is a periscope-shaped camera introduced by ATG. Like, that's not the same thing at all, right? So it basically hallucinated twice, which means that maybe you shouldn't really trust Sam Altman here, right? Because I think no matter what, he is going to tell you it's really good, because it's very, very important for OpenAI to succeed in the retrieval augmented generation kind of search space, right? Because the biggest behemoths in the AI world right now is a company like Google that owns search, right? And then a company like Perplexity, which is a startup, is trying to attack that search throne. And OpenAI really wants to dethrone Google, and to dethrone Google, you got to aim for the head, and to aim for the head, you got to get at search. So this is Sam Altman desperately trying to get search from Google, but unfortunately it just isn't quite there yet, because of the kind of hallucinatory nature of these LLMs, right? Where they kind of just make stuff up if you ask them a question where there isn't an answer, such as, where can I buy this, when I'm giving it a robot that it can't buy. Okay, so now that I've kind of established where RAG is right now and within the kind of zeitgeist and why it's important, I'm going to spend this stream, we're going to go over a bunch of different RAG papers. So for these streams, the sources I use to get my papers, you can come here into the docs repo and you can scroll down to the bottom here. And these are the different sources I use to find my papers. So for example, ML or Hugging Face, papers with code, and then Emergent Mind, right? So Hugging Face has this page here where you can basically go and you can see all the papers. You can see, looking at how many papers there are. There's literally like pages and pages of papers every single week released, right? Emergent Mind, I like this one for this trending page where you can come here and you can see, for example, the last 7 days, and it'll give you kind of how many X likes they had, whether it had any activity on Reddit. So it allows you to see what kind of the more popular, more viral, most recent papers are. Same thing with papers with code, right? They rank it based on the number of GitHub stars. But the reason I'm kind of showing you that is that these papers here that I picked for RAG aren't really necessarily the best RAG papers, right? We're at the point of machine learning research and kind of our progress towards the singularity, where the amount of machine learning papers that are being released is so huge that it's literally impossible for a human to put all of that into context, right? There's a limited amount of hours you have per day, and if you multiply the capacity of the human brain, right, the tokens per second of the human brain times the amount of hours you have in the day, it's like literally impossible to read every single paper in ML and to understand and read every single RAG paper. So what I've effectively done in this stream is almost kind of like a biological approach, where what I'm doing is I'm taking a sample of RAG papers, right? Where, hey, I'm interested in RAG, right? I'm like, oh, hey, RAG seems to be a thing now. You got all these big companies. They're all starting to release kind of RAG-based products. I'd love to learn more about RAG. Let me go and sample the population of RAG papers, right? Kind of like how you would go into a stream and then grab a little petri dish, and then you're just going to analyze the bacteria in that petri dish, and that's going to, hopefully that sample is going to represent the greater population of that stream. So these papers are in a way kind of like a sample, right? I'm basically just sampling all the RAG papers, right? So all of these were released this week, or just in the past couple weeks. We got 26th of October, we got 29th of October, we got the 30th of October, we got the 28th of October, we got the 26th of October, and we got the 28th of October. So all of these papers were released this week. but maybe there was a bunch of RAG stuff that came out like a month ago that I'm just unaware of, but it's too much for me to read. So I'm basically just taking a random sample here, and we're going to go through what the different ideas are and what the conclusions are in these different papers, maybe what they're focusing on, what they have problems with, what they don't have problems with, and then we're going to use that as a way to kind of better understand what is happening in this RAG space. Okay. How's it going? Brian, Sarah, ZZZZZ, Yatharth, and Aries. So starting with this one here, Vision Search Assistant empower vision language models as multimodal search engines. So this is coming out of a couple different Chinese institutions here. Frequently updating VLMs is impractical due to heavy computational burdens. So what they're saying there is that training a vision language model, because of just the larger size of images, right? Images being a two-dimensional grid of tokens when you feed them into a vision language model with a vision transformer, means that they just require a lot more tokens, which means that training and fine-tuning vision language models is more expensive than training and fine-tuning text-only models. So updating these VLMs, right? Imagine OpenAI, there's some vision transformer, some vision model that is consuming this image, right? They don't want to have to keep retraining this and releasing it every day, right? That would be very, very expensive. Maybe they want to do that every week or every month at most, right? So you want to limit the amount of times you have to keep updating these vision language models. So this paper proposes a collaboration between vision language models and web agents. Web agents are LLMs that kind of scrape through the internet or are capable of parsing kind of raw pages in order to create a vision search assistant, which leverages the VLM's visual understanding capability and the web agent's real-time information access to perform open-world retrieval-augmented generation via the web. And open-world retrieval-augmented generation via the web, that's effectively what GPT-4o with search is. That's what Perplexity is. And whenever you go to Google and you like type and then it has that little blurb that gets generated there, that's also retrieval-augmented generation via the web. Okay. So the important things here are whether your agent, right, which is a combination of a VLM, some LLM, a bunch of other fancy stuff here. We're going to see how all of these papers have this kind of agent loop or flow engineering flavor to them. So what I mean by like an agent loop or a flow engineering is that some human designed this flow, right? Or another way to think of it is like a kind of a graph or kind of like a state machine of like this process is going to happen and it's going to produce this artifact, and then this artifact is going to get consumed by these other processes, which are then going to produce these things, and then those things are going to be compared to this other thing. So what all of these papers are largely doing is designing this kind of flow, right? We're kind of like information flows in this way, and then information flows out that way, and there's a bunch of different nodes here that are connected in different ways. And I really like Karpathy's way of describing this as flow engineering, but a kind of a bigger, more abstract way to describe it would be something like an agent loop, right? It needs to understand the query, which is what the user is asking. It needs to decide which objects in the image it should look at and infer the correlation among the objects. So kind of like a little bit more advanced than just captioning the image with a VLM, right? So you're kind of doing kind of grounded captioning or sub-captioning, respectively generating the text to search, analyzing the contents returned from the search engine based on the query, and then judging whether the obtained visual and textual information is sufficient. So it's kind of like generation, right? Then retrieval based on that generation, and then kind of a filtering or judgment or kind of a summarization process on top of that. So for example, here they have a nice figure, and dude, Chinese papers have really good figures. Like, I don't know if it's a thing because like there's just more competition in kind of the Chinese machine learning paper world at this point, but the figures in Chinese papers are very good. Okay, so we got a nice figure here. We got different pictures. And what they're complaining about here is that vision language models show very limited generalization ability, right? Once you kind of train a vision language model on some pre-training corpus, maybe a little bit of fine-tuning data after that, it's a little bit frozen. So if you ask it a question that's a little bit more recent, it might not actually know what the fuck you're talking about. And we have here someone providing this picture, which I haven't actually played this game, but I know of it. It's called Black Myth Wukong. It's like a very popular Chinese game which came out relatively recently. And you can see here different vision language models. You have Lava 1.6, which is based on Llama. You have Qwen 2 VL and Intern VL2. All of these, you feed this image with this prompt, and then it gives you back this response. And every single one of these responses is wrong, right? So Lava thinks that this is Assassin's Creed. Qwen 2 thinks this is Journey to the West. Intern VL2 thinks this is Journey to the West, 7 Deadly Sins. So they're not even getting the video game right? So if you feed this vision language model this image, and it gives you the caption of the image, but the caption is wrong, as soon as you use that wrong caption to search the internet, then you're already wrong to begin with, right? So they're showing you here how, for example, their Vision Search Assistant, which really only is 7B, right? So there's a little bit of a hidden flex here where they're saying, hey, look at our 7B model outperforming these vision language models, which are bigger, right? 76B, 72B, 34B. It gets it right? So it can identify that that's Black Myth Wukong. So actually, I was a little bit curious, and I sent it to GPT-4o because I was like, oh, okay, I wonder if GPT-4o has the same problem, right? So please provide information about this game. I give it the same screenshot. It actually does get it. So that's interesting, right? So somehow GPT-4o with web searching is the way that it's extracting the information from this image. That is aware of Black Myth Wukong, the game, which means it's been trained at least in the past 6 months, right? When did this game come out? August 19th. I think there was probably some promotional material beforehand, so at least 2024, right? So at least we know that the vision language model that they're using in this is recent enough to be aware of that, or is good enough at providing grounded captions such that the text model that then goes, and the agent that then goes and finds this Wikipedia page is capable of doing that. But either way, I'm impressed with that. So I wasn't impressed with GPT-4o with Web's recognition of this robot arm, but hey, they're actually succeeding in the example that is shown as a negative example here in this Chinese paper. Okay. So what exactly is happening here? If we go a little bit further, yeah, this is the key idea here, is that visual content formulation, the open vocabulary detector is basically a image detection model. Usually detection models produce some kind of bounding box or some kind of segmentation mask, which is basically a way of saying this part of the image corresponds to this word that you gave me, right? The open vocabulary there means that you're giving it words that are not limited to some classification, because image detectors used to have a limited set of categories, right? Like something like a ImageNet classification model only outputs which of the whatever set of classes you have in that it was trained on, right? So open vocabulary detectors, which are pretty much standard now, right? Segment anything, all of these kind of more modern detection models generally support open vocab. But the key here is that it's creating these regions of interest in the original image, and then for each of those regions of interest, it's creating a regional caption. So if we go back to what the actual flow design here is, you get the image. This is your detection model, grounding Dino. Dino is, I forget who made Dino, but either way, right, it's detecting these two parts here, right? Obviously some kind of bounding box, and then for each of those, it's creating a caption. So you have a specialized region caption for A, a specialized region caption for B, and then those are used to then provide a better visual description of the actual image when you search. So for example, here when I'm searching with GPT-4o, I wonder if they did something similar, right? Where it basically, maybe it got the face and it said, okay, this is a monkey face. That must be the character Wukong, right? Because Wukong, I think, is not just from this game, it's like a general Chinese mythological character. So there's definitely been images of Wukong, just the mythological character, within the training corpus of the vision model here, but maybe not specifically the game. So it's at least capable of extracting that word Wukong. And as soon as you get that word Wukong, I think that should be enough to get the context of this entire game, right? So maybe this kind of similar region-based captioning as a way of better describing the image is something that the 4o web agent is doing. Okay, once you have these captions, then it's actually relatively simple. You basically are using some kind of web scraping agent. Here they're calling it web knowledge search, but you can see it's feeding this visual content. Has some kind of planning agent, right? This is all something that was designed by humans, right? So it breaks that down into event name, into time, place, and effect, and then it uses each of those to search, blah, 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 and you end up getting the summary, right? So it's a collaboration, as they're calling it, between kind of the vision language model and then a web agent. The LLM generates sub-questions. The web pages returned from the search engine are analyzed, selected, and summarized by the same LLM, and then we use the original image, the user's prompt, and the correlated formulation together with the obtained web knowledge to generate the final answer. Right? So you're basically, the user input is actually very minimal, just a single image and a couple tokens. And then in the background, you're expanding this out into, here's all this information here, here's a bunch of extra generated information, right? And then we're using all of that to search through some kind of database. And then we're going to summarize all of that. And then we're going to summarize all of that and condense it all the way down until the final thing that we give to the user, which is just this paragraph of text here. And according to them, and I mean, you never really know, but here's an evaluation. We conduct a human expert evaluation. Who is an expert at this? I don't really know, but interesting that they noted that. Significantly outperformed Perplexity AI Pro and GPT-4o Web. So here you have GPT-4o Web, which I'm pretty sure this is. This is GPT-4o Web. Perplexity is another one that people commonly use. And here they're actually basically saying that their Vision Search Assistant, which is just based on this kind of hard-coded flow engineering, and then their own Lava, right? This is all open source models here. So interesting that people significantly prefer Vision Search Assistant, which is this paper, over Perplexity AI Pro and GPT-4o Web, right? And it's starting to get to the point where it's like, what exactly does factuality and relevance and supportiveness even mean? You know what I'm saying? Like, they do have some examples here of how this is starting to become a little bit more nebulous, right? Which is, we're starting to see this idea of like, what is truth, right? And like, what do you want the agents to tell you given some potentially kind of controversial topics? So like here, for example, they bring up an example of how the different American model providers, right? So you have a representation here of basically the leading American providers of this kind of search-based intelligence. GPT-4o, Gemini, and Claude 3.5 Sonnet. You prompt them with a kind of a controversial issue here, which is kind of this political picture of Trump getting shot at, and then they're showing you how, hey, here in the U.S., like if you ask U.S. models that, they're going to give you propaganda, right? So you're either going to get the "I'm not allowed to talk of that" propaganda, or you're going to get the something else. I'm also not allowed to talk about that propaganda. But they're kind of positioning themselves as, hey, we are just going to give you the straight truth of it, which is kind of interesting, right? Because it's here in the US, right? There's this kind of narrative that China is very Orwellian and it's controlling its citizens, and like they're living in a content bubble where the government controls everything. But actually, with the small amount of time I've spent in China, they're getting fed the same exact picture of the US, right? So like they're getting told that the US is this propaganda state that kind of like filters what it feeds to its citizens. So like it's kind of interesting how the people in both nations kind of think that the other nation is the one that's kind of living in some kind of Orwellian situation. But all right. Weird, controversial stuff aside, let's move on to this paper here. All the heavy lifting workload was done by an LLM and embedding, isn't it? Kind of, yes, but I think let's go into these papers, because I think these papers kind of explain more of they paint a better picture to answer that question. Okay. All right. AutoMIR, effective zero-shot medical information retrieval, right? Medical information retrieval, that's what MIR is, without relevance labels. Okay, also from Chinese institution here. Medical information retrieval, and their specific approach to this is just called self-learning hypothetical document embeddings, which is quite a mouthful there, is a self-learning framework that progressively refines both pseudo-document generation and retrieval utilizing unlabeled medical corpora, right? So unlabeled medical corpora basically means you have just this giant database of medical text, but it's not labeled, it's not even filtered, right? It's basically just a bunch of raw plain text that you've scraped from some crusty medical database, right? So you're going to need to refine that or create from that a corpus of training data that you can use to train a retrieval model, right? And that's something that you're going to see pop up again and again and again in these papers. This is idea of a retrieval model. And let's quickly go here to a definition of exactly what a retrieval model is. So we're going to be bouncing around in these papers, but I don't think it's super important because, or it's not super important to remember which paper is which because all of these are kind of just presenting similar ideas. All right, so if we come here, where is it? I think it's this one. No. Every time. All right. I'm just never going to fucking find this, dude. Oh, here we go. Okay. The training of a retriever, or this retrieval model, generally has two stages. Unsupervised pre-training is where you have large volumes of unlabeled text to learn domain knowledge, right? So this first pre-training is just about getting a language model that has seen these tokens before, right? If you think about medical databases, there's going to be a lot of weird medical terminology. Like medicine is almost like an entirely new set of tokens that you have to learn in, right? Like there's so much vocabulary and terminology there that doesn't really exist in kind of the Reddit internet. So you probably, if you can have a retrieval model that's going to be working on exclusively this type of medical data, you probably want to just get it comfortable with this domain knowledge of medicine. But training on this kind of unlabeled, just giant dump of medical data is not going to be a way to get a very intelligent model, right? So we've seen this in pretty much every single type of deep learning based approach now, where you're splitting training into the pre-training stage on a higher order of magnitude size data set, but dirty. And then you have the fine-tuning on a cleaner, more manually verified, usually fine-tuning data set. So supervised fine-tuning on a high-quality labeled data set alongside hard negative mining. We're going to see what that is exactly to differentiate between similar texts, right? Because the whole point of a retriever model is to basically figure out which document makes the most sense for a given document, right? So there's sparse retrieval and there's dense retrieval. In this case, we're talking dense retrieval. And dense retrieval is about saying, okay, get me the document that is most related to this document, right? My user is asking this some question, right? That question is answered by some document. I want you to find in my database of medical documents the document that is the most related to that, right? So my retrieval model needs to be very good at differentiating between very similar texts. So just to give you some numbers here of the relative size of the unsupervised dataset versus the fine-tuning dataset, 800 million text pairs for the unsupervised stage, and then 3 million pairs for the fine-tuning stage. So 2 orders of magnitude difference there between the size of the pre-training and the fine-tuning dataset. Okay, so you have some user query queue, and that user query queue has some document that it should retrieve, right? So this is, now you're stepping into the stage of like actual labeled data, and labeled means that there's some corresponding label, some corresponding output to the input, and the output in this case is a specific document embedding, right? So you're saying, given this query, this is the document that I wanted, and I'm going to generate a fake document, right? And now we're going into this idea of pseudo document generation. So rather than taking your query, Let's see if there's another paper here that has a little bit of a better... this one has a similar idea, but rather than taking your query and then using that to search the database, you're going to take your query and you're going to use it to generate a pseudo document, and then you're going to use that pseudo document to basically retrieve or rank the documents that you have in your database based on that, right? So you're generating a fake answer and then saying this fake answer and the real answer should be very similar. And you can use this triplet to basically train a generator which generates hypothetical documents for the queries and constructs this labeled fine-tuning data set of here's your user query, here's a generated document, and then here's the document that it should have gotten, right? And once you do that, once you have this process of basically constructing these labeled data sets, you can employ what's called hard negative mining. Hard negative mining is when you create challenging negative examples that closely resemble the queries, right? So this is the full figure here. Let's go over this process in this figure. So you start off with some document, right? You select a pick, because the whole point here is that this training pipeline has to be automatic, right? They kind of want to create a pipeline that, or a flow that doesn't require human intervention and labeling and cleaning, right? So they want this entire training pipeline to be automated, and the point of that is that over time it's making better and better fine-tuning data sets, which means over time this is getting better and better and better, right? So the whole point of this training pipeline is to create a generator that is very good and to create a retriever that is very good. The generator is what's generating these pseudo documents, and then the retriever is what's finding appropriate documents based on that generated document. So this is what the user experiences. So this is the inference, right? So the user comes in, you have some query, the generator generates your document. That document gets used along with the retriever to fetch the most appropriate document, and then that's what gets sent to the actual LLM that then answers your question with that appropriate document in the context. And you can see that this is the training pipeline. So here you start off with a document, right? Because you have this giant database of medical information. You pick a random document, use that document to generate a hypothetical question, use that hypothetical question to feed it into the generator that generates a bunch of hypothetical documents to answer this hypothetical question. And then you have the retriever, which will rank all the documents in your database based on the hypothetical documents. It'll say, okay, these hypothetical documents, these are the documents that match most closely to those hypothetical documents. Now I have a pair that I can train on, where I say, okay, I have the query, hypothetical query, the hypothetical generated document. I also have the document that was retrieved, and I have documents that were retrieved that were low relevance. And then because I had the original document, I also have the original document that this query came from, right? So in a way, I already know what the answer is, right? So it's kind of like a self-supervised kind of setup here, where because you started off with a random document, you already know what the document it should pull should be, right? Because you generated the query from the document. So this creates effectively a labeled data set, and you can do this hard negative mining as well to say, okay, here's the query, here's the generated document, here's the document that you should have gotten, and then here's an example of a document that you shouldn't have generated or that you shouldn't have gotten. And you can tune both the generator and the retriever on this fine-tuning data set, and then you run that enough times and you'll eventually get a generator and a retriever that you can use that is specific to this database, right? So this is a general way, a automated way of creating a retrieval model and that can retrieve information for some kind of RAG pipeline for a database of things that is weird and potentially not even part of the pre-training corpus of a general language model, right? So that is this first paper here. Something interesting that I saw here is this is all using Chinese medical data. And I thought it was kind of interesting. In this part of the paper, they basically show all the different medical databases that they have available. And I thought it was kind of interesting how that if you actually look at the Chinese, I think this is probably Chinese medical literature or whatever, there's actually almost 3 times as much consultation data as there is literature data. I would have before I read this table, I would have actually thought it was the opposite. I would have thought that there was a hell of a lot more medical literature than consultation data, but it's actually the other way around. There's actually way more consultation data than there is literature, which I thought was kind of interesting and counterintuitive. Okay. All right, let's go into this one here. Zero-shot dense retrieval with embeddings from Relevance Feedback. Okay. Dense retrieval systems generate hypothetical documents that can be used to find the closest real document, all right? So starting to sound very similar to this one that we just read, right? This idea of generating a hypothetical document and finding the closest document in your database to that. However, this requires the LLM to generate a large number of tokens for each query. Ah, okay. So that's kind of interesting because that's a problem that these guys didn't talk about at all, right? Think about it. If in this inference pipeline right here, if you type in a question, and then you have a generator generate a hypothetical document, and then that hypothetical document is then used to retrieve, you have to wait for this generator to generate all the tokens in this hypothetical document before you can retrieve, which means the whole duration of this inference pipeline is actually kind of long, right? And that's what these guys are saying here, that maybe this hypothetical document generation, it's going to be a little bit slow, right? Can we make that faster? So they're proposing real document embeddings from Relevance Feedback, which is going to use an LLM to select which documents should be used for nearest neighbor search. And the key here is that the relevance estimation only requires the LLM to output a single token. Okay, so I'm calling this the minimum viable action, right? So here's the prompt. You are an expert judge of content using your internal knowledge, blah, blah, blah. Try to verify if the passage is relevant to the query. Here, 0 represents the passage, 1 represents that the passage is dedicated to the query and contains the exact answer. Okay, so they're basically, the whole TLDR of this paper is that, hey, rather than waiting on an LLM to generate this entire document here, this generated document based on your query, we can instead have an LLM that basically generates one token, and that token is just a number, 0 to 1, that basically just says, this is good, this is bad. So that's kind of in my mind, I see this as like the way that you sit there and you scroll on your phone, right? You're basically just providing one action that says not relevant, not relevant, not relevant, not relevant, not relevant, and then you'll click on something that's relevant, right? So the minimum viable action there is cheaper because each action is just a token, if you want to think of it that way. So having an LLM where the action is just one token like that means that you can do it a lot quicker or in parallel. So what they're doing is they're framing the task as a relevance estimation rather than a hypothetical document generation task. Okay. So in order to do that, you have your prompt, the LLM to mark return documents as relevant or non-relevant. It fetches the document embeddings, which are then pre-computed offline from the dense index. And then you basically determine whether those are relevant, right? So it's a little bit faster because it just only outputs one token. And that's largely the story for the other stuff in this paper as well, right? So if you look at it, the big success of this paper is that it's faster, right? So RDEF reduces retrieval latency by 7.5 to 11x. So you can basically get a 10x improvement in latency, which is effectively speed, like how quickly the system returns using this type of approach where you're using the LLM to basically quickly filter through things rather than generate and then search using that generation. So you can see here, 10x faster, 11x faster, 7x faster. Okay, pretty cool little idea there. All right, now let's go into this one. So you can see what I'm doing here, right? I'm basically just going into these papers and I'm trying to pull out the kind of the kernel of intuition that each of these papers have, right? So this first paper was really about, hey, you can generate hypothetical documents and use that along with a retriever with a kind of external database, and you can run this on the external database in this kind of automated self-supervised training pipeline such that over time you can create a very good generator and a very good retriever specifically for this database. This one here is saying, hey, if you're careful about how many tokens you have this LLM that is determining relevancy, then you can do something that's a little bit faster. Okay, what is this one? Coral, benchmarking multi-turn conversational retrieval-augmented generation. also out of a bunch of Chinese labs. I feel like it's kind of, it's getting weird to me where like, it feels like the majority of the papers I read are coming out of China, you know? There's probably something to say there. Coral is a large-scale benchmark RAG system for multi-turn information-seeking conversations automatically derived from Wikipedia. So multi-turn conversation is the norm, right? So what is a multi-turn conversation? This is a multi-turn conversation, right? Here's one turn, and then I'm going to ask a second question on the second term. So what these guys are saying is that, okay, well, actually, most of the RAG benchmarks, right, because this is really a benchmarking paper where they're like, hey, here's a benchmark, are basically single turn. So they're saying there's kind of a lack or a need for a multi-turn benchmark. And this paper is all about introducing a multi-turn benchmark. Multi-turn settings, systems must deal with redundant or irrelevant information from prior interactions and cope with abrupt topic shifts, right? So cope with abrupt topic shifts, right? So for example, right here, I asked it what black myth Wukong is, and then what have I said? What is the mitochondria the powerhouse of, right? That's an abrupt conversation. This is like an inside joke on an inside joke, but this actually did pretty well, right? It realized that, hey, this earlier part of the multi-turn conversation is irrelevant, so I'm just probably going to remove that from the context, right? So there's this idea of in multi-turn settings, you kind of have to be intelligent enough to know when you have to get rid of the previous conversation or not pay attention to certain things. So critical features include open domain coverage, which is handling questions from a wide range of topics, knowledge intensiveness, retrieving and generating deep contextual knowledge, freeform response generation, detailed, contextually rich answers, handling of topic shifts, sudden changes in dialogue context without carrying over relevant information, and citation labeling, which is citing the sources. And people are, I think, maybe over-indexing on this idea of citation labeling because even the citations are kind of garbage anyways, right? It's not like there isn't really a ground truth for most things in the world. Most of the stuff in the world, it's like it's very difficult to say what is true, what is not true. So this idea of like citation labeling of like, hey, I'm going to cite this random Reddit page, you know, it's not really helping you because you're just pushing the problem downstream. Because I'm still going to ask, okay, well, is that Reddit page correct or is that bullshit, right? Okay. So here's the Coral dataset construction process. Okay. So very similar to this here, right? This medical paper where they were constructing this fine-tuning data set, they're doing something similar here where they're basically constructing multi-turn Wikipedia conversations. So they start off with like a Wikipedia page, right? And you can go to any Wikipedia page, and this is what it looks like to you as a human. But if I go into here, right, this is what it actually looks like to an LLM, right? So what the LLM is seeing is basically this, right? It's just the data in effectively kind of like plain text. This is the web page in like LLM form, right? So this is what the LLM is seeing. And you can kind of use that as a structure or a bias from which to create these multi-turn conversations, right? So you can see that they pulled up the Wikipedia page on deepfakes, and then they can see this is header 1, this is header 2, this is header 3. So they kind of can create this knowledge graph of the information that's in there, and then they can say, okay, we're going to make a fake conversation for this. What is the deepfakes and how was it created? That's the turn 1. Then in turn 2, can you tell me more about the history of this technology? So they're like pretending to be a human that is asking questions. I would still argue that, like, do any humans really ask questions like this? Like, there's still a little bit of weirdness that is being introduced here because I wonder what percentage of user interactions in a multi-turn setting are actually similar to this, but you could also make the argument that the way Wikipedia pages are organized is based on this kind of human intuitive guess at what is the most relevant information. So maybe the inductive bias that Wikipedia has in the presentation of the information is exactly the same type of bias of humans in the way that they ask questions in a multi-turn setting. So maybe there's some kind of weird, like, synergy there in the way that the way that the knowledge graph of Wikipedia is organized actually is very similar to the way that people ask questions when they're trying to learn things. But that's really what this paper is basically they just sift through Wikipedia. Here's 4 different ways that they create these conversations. So you have, these basically are just different types of graph traversal tech ways, right? So you have breadth first search, depth first search. You have kind of like everything in between. You have linear descent sampling where they start with here, then go to impacts, then go to humans, then go to, so it's almost like a depth first search. Here you have sibling inclusive descent sampling. There's almost like a breadth first kind of search, right? You see how it's going all the way across first, and then it's going deeper but across. And then you have something kind of weird like dual tree random walk, where you go down the knowledge graph, back up the knowledge graph, back down the knowledge graph. And really they just want to sample uniformly, right? Because they don't really know what the correct prior is for this, because you don't really know what human behavior is like for these multi-turn conversations. So they're kind of just assuming that, hey, we just sample uniformly across the space of all possible walks through these knowledge graphs. That's going to hopefully be good for creating a data set that we can use to benchmark RAG systems in multi-turn conversation settings. And they have about 11 to 20 turns per conversation, and it's about 8,000 conversations. So kind of a small data set, but it's more of a benchmark anyways, right? You're not supposed to be really training on this. You're supposed to be evaluating the models on this. Okay. Yeah, unfortunately, the models that they use to compare are not like super interesting. They're like these little tiny models. So, yeah, Llama 3.1, Mistral, like, you know, these feel old at this point. You know, like who is actually using Mistral 7B at this point? But, okay. That's that paper. Holy shit. Unsupervised universe. What are you mashing here? Will RAG go away when max context length becomes long enough to handle hundreds of documents? That's something that I've said before, so that's a very good question, NLP Uniform. Is as the context length gets bigger and bigger and bigger, right? Like, do these pipelines simplify, right? Right now, the reason we have to do this kind of flow engineering is because there's limitations on the context for all of this, right? So just think about it this way. When you're doing this grounding dyno, right, and you're producing 2 different image captions based on regions within the image, at some point, the vision language models are going to be, the context size for that is going to be so big that when you give it a single image, it can produce a 10-page document about this image. And that 10-page document is going to include literally every single possible piece of information from that, right? And that 10-page document, once these agents, these LLM agents have a bigger and bigger context size, then it's totally okay to give them a 10-page document, right? So like as the context size increases for all these things, you probably can get rid of some of these in-between steps, right? So yeah, there is something there. I just don't know if that's necessarily going to be the case. Let's go to this one. Beyond text, optimizing RAG with multimodal inputs for industrial applications. So LLMs lack domain-specific knowledge and are prone to hallucinations, which we saw firsthand, right? Here is a LLM which doesn't really have domain-specific knowledge of robotics. So when I ask it, hey, here's a robot arm, it's just like, okay, here's a robot arm, right? It doesn't have the domain-specific expertise to like understand that this is a different arm than the Boston Dynamics Spot arm, right? Okay. So in this paper, they're going to be doing a series of experiments on how to best integrate multimodal models into RAG systems, specifically around this idea of image processing and retrieval using GPT-4 Vision and Lava, which are a little bit outdated now, but multimodal RAG can outperform single modality RAG. Image summaries offer a greater flexibility and potential for advancement. All right, so they're testing out effectively 2 different ideas here. One idea is what they call multimodal embeddings and separate vector stores. So separate vector stores means that you see here how there's 2 vector databases, right? So when you're performing retrieval, what you're really doing is you're looking at the similarity between 2 vectors. I had that section labeled somewhere, but I just can't find it anymore. Is it this? But you're basically comparing this embedding with embeddings in your vector database. Your vector database is a database that's indexed, or basically the lookup, what you're using to like find things is a little vector. So you have to go through that entire vector database and find the items in the potentially thousands and thousands of rows that are the most similar to this embedding. So you're basically doing a bunch of little similarity calculations. Hey, is this vector similar to this one? No. Is this vector similar to this one? Yes. Is this vector similar to this one? Yes. Is this vector similar to this one? Right? So the more of those you have to do, the bigger your vector that you're using to compare, the more compute it's going to take to do that little calculation, the longer it's going to take. So like with any of these things, there's this trade-off of like how fast it's doing it and how accurate it is, right? And those are kind of always at odds with each other, where the more accurate, the bigger you're embedding, the more carefully you're going through every single thing, the longer it's going to take. So you kind of want it to be very fast, but also correct enough that the user continues to use this, right? So in this split or separate vector store approach, you take your images, you encode those images, and you take your text and you encode those texts, but these are different types of embeddings, right? And then you're using those to search a separate image database and a separate text database, and then you're combining those together, right? So call this the separate vector stores. A different way to do this is using image summaries in a combined vector store. So you extract the images out, you turn them into a text, and then you use that text to get a text embedding. So now you've turned every single image into these image summaries, or basically image captions, or effectively text embeddings. And now you can store both the image text embeddings and the text embeddings in the same vector database, right? So now everything is just in one database and you're searching it with text embeddings, which is similar to the approach here, right? This is basically the same approach where, hey, rather than searching using images and image embeddings to search a database of image embeddings, right? Let's turn the images into text and then use text to search text information, right? So using text to search text seems to be a little bit faster, a little bit better than using images to search images. And that's really what they're showing you in this paper as well, is that they're basically saying that, hey, image summaries, they call it image summaries, but it's effectively just this idea of turning images into text and then using the text to search text. That's better. And here, let me see if there's one thing here. So here's the results for this paper. And I think the results aren't like particularly strong, but here you see the answer correctness. So there's the whole purpose of a retrieval of a RAG system is to give you a correct answer, right? Is to give you the Black Myth Wukong answer, right? Give you the correct answer. So here, the higher the answer correctness, the better the RAG system is, right? So they have the baseline, no RAG. So this is just zero shot. You're just giving GPT-4o an image of the Black Myth Wukong and asking it to answer that just with nothing, right? Like no search. Actually, I wonder what happens if you do that. Can I turn off search and save image as? Save. Like if we just do GPT-4o without search and we just upload that image. Oh my God, dude, this is such garbage. This one. What is this game? Let's make sure it's the same exact question. What's the question here? Provide information about this game. There you go. Oh shit, it got it. So actually, this is actually confirming some of our theories here, where it recognizes the Chinese mythological figure Wukong, but then it somehow also knows about Black Myth Wukong. So I don't know. That's actually kind of impressive because it means that GPT-4o, like, it doesn't even need to do RAG, right? That's basically this. It's baseline, no RAG. That's just the model itself, which means that it's getting updated, right? They're pushing gradients into that, or it's not actually what I think it is, right? The other side of that is that this also has some context that we're not aware of, right? Because OpenAI is very closed. They don't actually tell you what's going on here. I believe I'm just putting this image and then putting this text, and that's being fed to some kind of language model, and then it's outputting, but that could be not the case, right? There could be RAG happening behind the scenes here that we're not entirely aware of. But back to this paper, right, where they're basically saying image descriptions, and you can see here, okay, image-only clip, image-only summaries, text-only, multimodal clip, multimodal summaries, multimodal clip and multimodal summaries perform better than this baseline, and then image-only clip and image-only summary. So it's not like outrageous, and they do it with a couple of different models here, Lava, GPT-4V, and GPT-4V. And then the same way they have kind of like a low threshold baseline, they also have what they call gold context. And I had to scroll up here. Gold standard, we directly provide the annotated context from the test set along to the LLM along with the question, skipping the retrieval step. This setup serves as an upper bound. So here, right, they basically know what the relevant document is, and they're saying, if we gave you the relevant document, how good would you answer that? So that's basically saying, okay, if we gave you this question and we literally knew that it was Black Myth Wukong, so we literally give you the Wikipedia page for Black Myth Wukong, how good is Lava performing at answering your question? So it's a little weird that it still doesn't even get 100%, right? It still only answers it like 70% of the time or 60% of the time correctly, even when you give it the full like Wikipedia page with the image and everything. But the main thing is that this here is better than this, right? These three here are better than these here, which is really the key result of this paper, which is this idea of, hey, turning images into text to then search with only text embeddings, and everything is text embeddings. And if you have an image, you turn it into image summaries or text. Okay. Now let's get to the last paper. RARE, Retrieval-Augmented Retrieval with in-context examples. Whether in-context examples can improve embedding model performance in retrieval. RARE fine-tunes a pre-trained model with in-context examples whose query is semantically similar to the target query. Okay, so inference-only modification does not work. Adding in-context examples to the query without updating the model parameters, embedding models generally exhibit decreased performance when in-context examples are added. So embedding models, that's the model that's turning your piece of text into a text embedding. So this part here, or this step here, where you're turning your text into this text embedding, right? That's also being done by a transformer. And here they're saying, hey, that transformer, what if we augmented that retrieval with retrieval, right? So it's kind of like retrieval squared at this point. They're basically saying we're going to add in-context examples. In-context examples basically just means when I'm asking you to go find this document or produce some embedding, or I'm going to give you within the context, not just the document, but also a couple other examples of like, hey, given this query, this was the document. Given this query, this was the document. Given this query, this was the document. Here's a query, and then you're asking it to send the document. If you do not fine-tune that retrieval model for in-context examples, then it's actually going to decrease the performance of that, which actually makes a lot of sense, right? If you have a retrieval model, that model is like kind of fragile, right? It's like this, let's go back here. This little retrieval model, like anytime you take a language model or any kind of deep learning model that's been trained on a very wide distribution, and you start fine-tuning it or pushing gradients on a much narrower, lower variance, kind of tinier distribution, it starts to kind of catastrophically forget some of that generalization capability that it used to have, right? So models that come kind of right, and this is something that people have started noticing as well with things like instruction tuning, right? Where whenever people train models to perform this type of behavior, right? Like the Gemini, I can't help with responses on elections or blah, 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 right? This model is going to be stupider because of that, right? So a similar kind of thing happens with these retrieval models where once you start pushing gradients that force them into this kind of very narrow type of intelligence, which is this kind of retrieving or creating embeddings, then the ability to add in-context examples and generalize to using those in-context examples to improve, that basically is no longer there, right? So for something fragile, like an embedding model or a retrieval model, if you start putting in a bunch of shit in the context, like these in-context examples, it's just going to make it worse, right? So this paper, really what the TLDR for this paper is, they fine-tune the retrieval models or the embedding models such that they have the ability to add in-context examples. So it's, like I said, it's literally inception squared, because what they're realizing is that, hey, this model right here, this retriever, what if we also gave it, rather than just providing these things as context, we gave it like 4 other things that were examples of how to get good documents. And we fine-tune it on a data set that has a bunch of in-context examples, so that whenever you actually run it in the inference pipeline, it's expecting in-context examples. So we can give it in-context examples that hopefully help it perform better at this retrieval or embedding task. And so again, TLDR here, equips retrievers with the ability to leverage in-context examples by training with semantically similar in-context examples. But unfortunately for this paper here, it's kind of like a bit of a not negative result paper, right? So a negative result paper is a paper where you have some kind of hypothesis, you test it out, and the results aren't that great. And here's what I mean by that. So for example, in context, compare invariance of in-context examples. So instruct refers to the baseline, which does not use any in-context examples. So what they're trying to beat is this one here, right? They're trying to say, okay, if we fine-tune this retrieval model with in-context examples and then give it in-context examples, that should perform better than just a model that isn't fine-tuned on that and isn't provided with that extra information. And the difference really is just not there. This is what I'm saying, right? It's actually, like, depending on some benchmarks, so for example, SciFact, which is some kind of science fact-based benchmark, I'm guessing, I don't actually know for sure, it does significantly improve it, right? You're almost getting like a 10-point improvement here by adding these 10 in-context examples in the retrieval model. But that's not the case across the board, right? And you see a bunch of other benchmarks here, Argu, ANA, FEQA 2018, SciFact. For these ones, it actually almost makes it worse sometimes, right? So that's kind of what I mean by this being a little bit of a negative result paper, which is fine, right? I think that's just part of scientific progress, is that you're going to test a hypothesis, and sometimes the hypothesis isn't correct. And ideally, you want to write a paper on that and publish it so other people can read that and then realize that this wasn't that great of an idea, so then they can save time, money, and effort by not pursuing that idea themselves. So I think that negative result papers are important, and that's why I'm including it in this stream, is because, hey, look at that. It actually didn't make much of a difference here. So maybe we shouldn't be adding a bunch of in-context examples and fine-tuning these retrieval models for the in-context examples, because it doesn't really seem to improve performance that much. And if we go back to this thing, if anything, it's increasing the latency too, right? Because adding those in-context examples, that means that this model here, right, the retriever, it actually has to consume more tokens, right? So when you have more in-context examples, this step right here of the retrieval is going to take longer. So there's no point in adding more latency in that inference pipeline, more compute that you have to perform for something that isn't even giving you a higher performance. Okay. Thoughts on Cole Pally? I don't know what that is. Let me search it up. Cole Pally. Efficient. Let's go to here. This is probably a nicer little summary. Efficient document retrieval with vision language models. Run OCR. Run document layout detection. Reconstruct the order. Just embed the page directly. Okay, so these guys are basically saying kind of a similar, kind of the anti-energy of this, right? So this paper is all about like, hey, extract all the different regions and then summarize each of the regions and then use that to like create this long document of all the possible different things that you want to search for. So this is like expanding. It's basically taking the information that the user gives you and then just exploding it into this giant amount of text and then using that giant amount of text to then search. But this one is just the opposite idea, right? Which is this idea of like, hey, turn the image into an embedding and then use that embedding to search probably some image database. Yeah, so you see here, 30 milliseconds per query versus 22 milliseconds per query. You're taking the entire, okay, this is kind of intense. So you see here, they're saying standard retrieval. And in this case, you're taking the PDF, you're doing OCR, optical character recognition, you're extracting all the text, and you're feeding that into some text embedding. You're extracting the images, possibly feeding those into image embedding models. But you see here, what they're doing in ColPally is actually way simpler. They're just chunking the entire PDF into 4 images and then feeding each of those 4 images into just a giant image encoder and then getting some similarity vector from that. I guess they're doing 4 different similarity vectors here, or 4 different embeddings for each of the 4 different patches in this image. And then using, here's your retrieval process, right, where you're basically trying to find the green embedding vector in your database that is as fast as possible or as close as possible to the, actually I think it's the opposite. This is the user query. User query is being broken down into text embeddings. Those text embeddings are being used along with some kind of similarity metric, like a cosine similarity, to search for the right embedding to then get this particular piece of information and then add that to some RAG pipeline, right? And part of the whole point of this, you see how it says offline, is that all of this, right, the creation of these purple vectors can be done all offline, right? And that's very similar to what they were doing here in this one, right? Where why is this faster is because these can basically be created offline, right? You can create all these documents offline so that whenever you're just comparing these documents, or even in this one here, right? This vector DB here, all the images in your vector DB are already stored in that vector DB with an embedding vector that has been calculated, right? Calculating this little red vector from an image, it takes some amount of compute and inference. So you don't want to have to do that for every single image in your vector DB. You just having that embedding and then just using similarity to compare those embeddings is significantly more computationally efficient because you can basically pre-compute all these little purple embeddings, the little offline here. Okay, but that's basically it. Let's see these results. Okay, I mean, they perform better, right? That's what this row down here is telling you. They're better at whatever these different benchmarks are here, but what are they really comparing to here, you know? BiPally, SIGLIP, GinaClip. Ooh, here's a little, right, when you consume an image with a vision transformer, it's chunking it into little tokens, which are patches, right? And then you can always go back and look at the attention of the transformer, right? The transformer is looking at which elements in the sequence or which patches in the image are paying the most attention to the whatever other text you want there, right? So you can actually see which parts of the image are paying the most attention or have the highest attention score with the text for this. And you can see that it's actually paying attention to the numbers here, some of the stuff here. Which hour of the day had the highest overall electricity generation? Interesting. LLMs need RAG when tasked with current event questions. It's a question or a comment from Raja. Kind of, but I think to answer that or to comment on that, it kind of boils down to this paper, right? So in this paper, what are they kind of fundamentally really trying, or like kind of comparing here, right? What they're comparing here is the idea of like, if you put shit in the context versus if you push the gradients, right? There's a difference between, okay, I have relevant information, I'm just going to add that information to the context, versus I have something where I've been pushing that information via gradients, right? I'm actually training that into the model. So when I think about the future, I can see both of those working, right? I can see a world where the context length gets really, really big, and it gets really, really easy to just put all the relevant information in the context. At which point, you probably have very intelligent models that are rarely trained, right? They're maybe trained once a year or once or twice a year, and then all the relevant news information is just put into the context. But I could also see a completely different future where fine-tuning and actually pushing gradients is more effective, and in that future, very little information is actually put into the context of the model, right? Which makes it faster in inference. But you spend a lot more compute constantly pushing gradients into these models, right? So then the foundation model, there might be like a much faster cadence, right? They might come out every single week, because every single week they have to take all the news from the week and they have to create a little data set from that. Then they have to push those gradients into the fine-tune the base model with those gradients. And then the fine-tuned base model is what you're interacting with, right? So every single week you're interacting with effectively a new model. So there's a little bit of a trade-off between both those futures, right? In one future, you're paying more for inference because you have to basically put more and more shit into the context. But in the other future, you're paying more during training because you constantly have to retrain your models every week with all the new data. And it's not entirely sure or certain to me which one of those two is better, right? It really depends on a lot of things. It depends on kind of what types of queries are people going to be asking people. Are we going to discover any types of new algorithmic or kind of architecture-based things that make long context better? Are we going to figure out better ways of pre-training, right? Are we going to figure out, it comes down to the hardware too, like is it the case that the training clusters are just so good at training that it's okay to just constantly train on the latest news? Or is it that the training clusters are just so busy training the next foundation model that you'd rather just take the hit by keeping the foundation model largely frozen and then just putting all the relevant news information into the context, in which case you're paying more on the inference, right? I could see both of those working. Especially with prompt caching. That's a good point, Ankit Savio. If you account for prompt caching, that would be a reason for that would be more evidence for this future where like the base model rarely ever changes and mostly what you're doing is swapping in the in context. Yeah, continual learning is another term used to describe kind of this idea of like actually pushing gradients in, right? So like rather than just taking a foundation model and just adding a bunch of shit in the context, you basically are actually pushing gradients maybe every single week, maybe every single day, like maybe every single hour, right? Imagine some kind of weird future where all these training pipelines are automated to the point that like every single hour it just takes the latest news and then just creates a batch of data, pushes those gradients into that model, and then deploys that model across all the inference endpoints, right? Okay. I think that's pretty much most of what I wanted to talk about. Let me see if there's any other questions here. What's the best embedding model? How much does the quality improve with more dimensions? So in general, the size of your embedding is kind of like the capacity of your embedding, right? So like the here it's just 3 little boxes, right? But it's obviously going to be more than that. Maybe it's like 128 dimensional, 1,000 dimensional, right? 100,000 dimensional. As the size of that embedding increases, the information representation capacity of that embedding space increases, right? So the higher dimensional that space, the more information you can cram into that space, which means that the better any kind of information retrieval that is using a similarity metric between those two vectors will be able to perform. But the problem is that it'll take longer, right? So the bigger this vector, the longer every single little similarity calculation will take, right? The more memory it'll take on the database. Everything will just take slightly longer, more memory. But over time, as our computers get faster, the computers that are storing and computing for these vector databases, the memory gets bigger and bigger, right? As those get bigger and bigger, you can expect the sizes of these embeddings to also grow. Unsupervised universe. I'm sorry, man. Like this is like 10 questions in a row. Like I'm just not going to answer any of that. Keep scrolling. What do you use for reading the PDFs? This is a product called PaperPile, but it just, here, I can go on to the PaperPile page. It's just like this. It's just like a document organizer. You know, you can sit there, click on PDFs, annotator. It's a good product, but they don't pay me at all, you know? So I'm tired of constantly referencing them. There's other ones, though. There's Mendeley is another one. Kami is another. There's like literally a dozen different PDF annotator products. So like it's not, this one I just use because it's convenient, but I'm not saying it's the best. I'm not even saying I've tried all of them and this one is the best. Zotero, is that a different one? Zotero. Personal research assistant. Oh, look at that. There you go. I like literally had never even heard of this. So there you go. Maybe I switched to that. I don't know. If you're part of a PDF annotation company and you want to sponsor this stream, I feel like that's a sponsor I would be okay with. As long as the product is good. I'm not going to sponsor some shit product. Okay. I'll probably end it there. I feel like I talked mostly about everything. Maybe there's one more thing that I had here prepared. So what is RAG, right? Like I started off this stream by saying RAG is a very large umbrella term to describe any kind of generation where you are retrieving information from some kind of static place and then using that information to improve the generation, right? And that's a very generic definition, and I think it applies to pretty much everything, right? And you can go all the way back even to ideas such as here we have the von Neumann architecture. This is the guy back in 1945, sometimes called like, I don't want to say the father of computing because this guy Turing was also very important, but look at this sketch, this little sketch here, right? This idea of you have an input device, you have some kind of arithmetic logic unit, right, with this, which is the generator part, and then you have this memory unit, which is storing information. And then the arithmetic logic unit is retrieving stuff from the memory unit and then using that to generate output given some input. That's RAG. You know what I'm saying? Like this is effectively RAG. And if you want to go even more basic than that, we can go to the Turing machine, which is an even broader definition. And at the point of a Turing machine, you just have like two elements here. You have this idea of a tape, right, which actually refers to literally the way that the initial computers were, where you had this tape of information that was just passing through this head, and the head is reading the information from the tape, and the head has some kind of storage within it, and then it's writing something out or producing some output, right? And if you really want to take a step back from that, really what these are almost like formal definitions of kind of space-time is the way that I think about it, right? Where really what is this describing? Is describing our 4D reality, right? Where we have 3 dimensions of space, and you can think of the 3 dimensions of space as roughly kind of like a memory, right? Where it's like, okay, there's these 3 dimensions of space, and I can store an object in this 3 dimension of space with 3 numbers that represent basically its location in space, right? So there's some location where I can put things and I can retrieve things, right? In von Neumann architecture, it's the memory unit. In the Turing machine, it's the head. And then just in my kind of even more generic version of it, it's space-time. It's space. And then you have time, which is where your kind of sequence formalism comes in, which is this idea of, okay, there's this stream of things happening, and you are aware of the things that have happened before, but then you don't know the things that are coming out in the future, right? So you're basically saying there's this kind of flow of time, and the flow of time also exists here, right? The input is coming in at some cadence, right? So that's kind of like the time dimension, and then the memory is kind of the space dimension, right? So I don't know. I just thought it was kind of cool to like realize that retrieval augmented generation is really just the more modern reframing of kind of the basic ideas of computer science, which are this idea of like you have memory or space where you can store things and you can retrieve stuff from that storage to improve the way that you consume the input, right? You have this flow of time that is producing a constant stream of things that you can pay attention to. And whenever you pay attention to those things in time, you are retrieving from your memory or your spatial area where you're storing things, retrieving relevant things, and then using that to write out something, right? So it's like everything, I don't know, just these hierarchies of mental abstractions in my head I thought are kind of cool, but I realize it's a little bit of a digression from our discussion. All right. We're all just abstracting from a Turing machine all the way along. That's true. All computer science can basically be thought of as just Turing machines. It's really just the same patterns over and over again. And then people just come up with a new name for the pattern so that they can feel like they did something novel. All right. Let's do a summary of the stream. Dude, I wish this hat wasn't see-through. It's a little Yoda hat for Halloween. All right. Today's stream was called RAG. And in today's stream, I sampled a bunch of RAG papers from the machine learning river, right? There's this river of machine learning papers that is just constantly spewing out papers. So I'm not saying these are the best RAG papers. I'm not even saying these are the most relevant RAG papers. I just kind of randomly sampled some RAG papers here, and we read through them to kind of get an idea of like what the different problems are, what are people focusing on, what are the different hypotheses that people have within the RAG space, because this space is it's popular right now. You know, you got Sam Altman trying to dethrone the king. You know, he's trying to make Perplexity die. He's trying to make Google die. And in order to kill Google, you got to kill search. So that's what he's going after right here. And they've released this GPT-4o with web search. But there's a problem, guys. The problem is that it's a little bit hallucinatory. You know, it's had a little bit too many mushrooms. It's tripping. It doesn't know that this is not a Boston Dynamics spot arm, right? So it's a little bit rough. The products just aren't quite there yet. We read this paper here, Vision Search Assistant. This is a Chinese paper where they basically use what they call regional captions, right? They break an image into little detection areas, then they caption each of those detection areas. Then with each of those caption detection areas, they further expand that text into even more text. And then now that you've kind of exploded this user question with a ton of text, your searching agent or your retrieval model, as they're calling it in these other RAG papers, can retrieve more relevant information. And then with this more relevant information, a language model can give you an answer to your question, right? And apparently this is better than Perplexity or GPT-4o plus Web, maybe a little bit of bias. We also looked at this paper, AutoMIR, Auto Medical Information Retrieval. In this paper, they create a self-supervised automatic training pipeline where you can provide just a giant database of random documents that are potentially very weird, very esoteric, have a lot of vocabulary and terminology that isn't common in pre-training corpuses. So here they use medical data, but it could be anything. It could be like aquarium hobby data, or, like something weird like that, where it's like you're not really going to find a lot of it, so the LLMs aren't going to answer good questions on that. And in this automatic kind of self-supervised training pipeline, they sample random documents from that database. They create fake questions. They use those fake questions to generate fake documents that answer those fake questions. And then they have a retrieval model which tries to find the most relevant documents given these fake documents that were generated from this fake question, and it retrieves those. And because you've now created all these fake things, you've created a fake data point, right? This fake data point is a fake question with a fake document that was generated, the real document that it came from, and then a document that is not related at all and kind of like a negative example. Like, this is definitely not a document that you should have retrieved given this fake document. And you've now created a little data point that you can use to train and improve your generator of fake documents and your retrieval of documents. And you can run that over time. You can just let it run on your database, just sit there, just slowly over time improving this tune generator and this tune retriever. And then once you have that, now you can have this nice little inference pipeline, or this nice little experience where a user can come in, type a question, that question gets turned into a fake document, that fake document gets used to densely search a database using a retrieval model, which will use some kind of similarity metric between two vectors to find an appropriate document. And then that document can be used to augment the generation to answer the query, right? So that's AutoMIR. Zero-shot dense retrieval. This is the same idea, generating hypothetical documents, but in this case, rather than generating kind of full documents, it's just determining whether or not the document is relevant. So basically, it's outputting a single token that says this document is relevant, this document is not relevant, this document is relevant, this document is not relevant. So basically trying to cut out this part in the pipeline, right? Trying to get rid of this part here where you have to generate an entire fake document to do dense retrieval. And that allows you to get like basically a 10x speed up in the latency when the user is interacting with this RAG system. You got a benchmark for multi-turn conversations that is synthetically generated from Wikipedia, basically traversing Wikipedia knowledge graphs and creating these fake 10 or 20 turn conversations so that you can benchmark RAG systems in multi-turn conversations, because there's a lot of nuance here that you want to be able to do, right? You need to be able to deal with sudden changes in dialogue context. You need to handle questions from a wide variety of topics so people can ask weird questions that might seem unrelated one after the other, and you have to be able to handle that and ignore things that aren't important. We have beyond text optimizing RAG. This is basically a simple experiment where they look at, should we turn images into text and then turn those text into text embeddings so we can have a single database of single vector database where everything is indexed based on that vector and everything is indexed based on effectively a text embedding? Or should we have a separate vector database for images and a separate vector database for text? And they compare here. For example, why do they have CLIP here? Because CLIP is a contrastively trained model where the image and the text embeddings are kind of similar. So like the CLIP embeddings here are going to be, if you used CLIP to encode this and this, these would be kind of similar-ish, right? Versus if you do it this way, you don't have to use a CLIP model here. You could use a different type of vision language model that just produces text and then use the same text embedding model to embed both of these. It gets a little bit better performance, but it's honestly not super amazing result. This one here Retrieval-Augmented Retrieval, also not a necessarily amazing result, but they tried this kind of crazy idea of fine-tuning the retrieval model such that it can use in-context examples. So they want to basically take this retriever and say, hey, what if we added in-context examples here? Would that improve the performance of the retriever? And kind of unfortunately is it doesn't really improve it that much. Maybe for some things like science, but for kind of most things, it doesn't necessarily help that much. But that's basically it, guys. That's where RAG is at in whatever this is, November 1st, 2024. It seems like we're getting there. You know, it still feels like there's a lot of different ideas, right? When I look at these papers, a lot of different ideas, right? So people are definitely still exploring the space of what RAG is going to look like. And it'd be really awesome if we could actually know how OpenAI does it, right? Like, how is the RAG here working, right? Like, really, what are the different databases you're using? Like, how are you storing things in these databases? What models are you using to embed the image? Are they doing this type of text caption or text summarization for the images? Are they just searching directly using the image embedding? Like, I'd be super curious to see if there's any secret sauce on their end, but the fact that they're getting beat by this random open source Chinese paper tells me that maybe they're not really the bleeding edge anymore, right? And maybe Perplexity and the people at Perplexity and GPT and OpenAI are no better at RAG than these guys, right? And they just created their own complicated human engineered pipeline to do RAG, but it's not really any much better than everybody else's complicated pipeline that they made, right? So all I see is complicated pipelines and lots of different ideas, which means that there isn't necessarily a winner in this race yet. All right. What do I think of DSPy, Meet Pro, V2 Optimizer, and such? I don't really use it. I think somebody else was trying to hype that. Thank Invisible Yoda. My whole head is invisible now. Look at that. All right, guys, that's pretty much it for today. Hope you enjoyed the stream. Hope you're thinking about RAG, and go out and test these different RAG systems. Go out and test Perplexity, test GPT-4o. See if you guys can find situations where they hallucinate. But yeah, have a good weekend. See you guys later. Thank you, NLP Prompter, ZZZ, Yatharth, Sarah, MWD, Kaito, Harsh, Master FX 2000, Explorer, Ankit, Tuan, Cheb Khaled, Pulkit, Raja, Unsupervised Universe, Brian, Aries, Stalin, Pratik, Ecox, Ryan, Sarah, Cheb. Thanks everybody for listening. Have a great weekend. See you guys later.